appreciate it. It's a quite interesting topic that you know that half of the people of my institute works in mining related research line. So someone like you with your expertise and with your knowledge is most welcome in this kind of internal seminars. So for the benefit of the rest of the people that didn't know you, let me give a brief abstract of your curricula. Phil Metzger is a planetary scientist at the University of Central Florida. His expertise is in technologies for space mining, construction, and resources processing. He was previously at NASA Kennedy Space Center, where he co-founded the KSC Swarm Workers, if I am pronounced it correctly, a technological innovation hub for planetary surface technologies. And while at NASA, he led the agency's work in rocket blast efforts for human class missions to the Moon and Mars. He received the Astronaut Silver Snoopy Award in 2010 and was elected as the Kennedy Space Center's NASA Scientist Engineer of the Year for 2011. He was also awarded the NASA Silver Achievement Medal in 2014 for technology development, quite impressive. The American Society of Civil Engineers Aerospace Division selected him for the Outstanding Technical Contribution Award in 2016, and he became a NASA Innovative Advanced Concepts Fellow in 2019. So I'm pretty sure that you have even more achievement than this. This is only an abstract, a selection, but as everybody wants to hear you and not my horrible English accent, please Phil, thank you again once more for being here, and whenever you want, we are so looking forward to hear you.
Thank you, Javi. It's my pleasure to speak with you all. And I'm sorry I cannot speak in Spanish. I have been trying to learn for 3 years, but at my age, it's harder to learn languages, so I'm too slow. But anyways, so let me share my screen. How do I do this? I need to figure out how to share this. Oh, I don't think it's.
You are able to find the microphone and the camera to set them up and down. You can find just right there.
Yeah, it says only meeting organizers and presenters can share.
Oh,
you have to promote me.
Only we need to grant him access to the press. And I don't know. Chiqui, are you there? Anyone else? No?
I am there, but it's not easy.
So we are working on it. Okay.
Okay. So while you're doing that, I'll say that I started doing research on this topic in 1997. So it's been 24 years of research.
Wow.
And at the time I started doing this research, I think I was the only person in the world studying this topic. The reason I started working on it, oh, there we go. Okay, so I'll share the screen now. The reason I started studying this topic was because I was part of the team at NASA that wanted to, I'm just gonna share my, well, let's see, share a window. And I'm gonna share my whole screen because I need to switch to some videos. So, okay, can you see my screen?
Yes, yes.
Okay, close that. Okay, too many windows are open. Okay, let's see, Microsoft, where is Microsoft? There we go. Okay, so I was part of the team working on using space resources, and we wanted to be able to land a rocket near the gas station on Mars. But in order to do that, you have to land close enough without damaging your gas station. So I started to study how does rocket exhaust blow soil, and that ended up being my whole career. So I did my PhD research on this topic, sort of. I ended up doing a dissertation on theory about granular materials, but a lot of my PhD research was on this topic. So I like this picture. This was a recent SpaceX flight in Texas. Obviously, it's not the moon, but I like it because they're so high above the ground. You see the core of the rocket exhaust, supersonic jet, only goes to about this far, and yet look at how much dust they're blowing. But here we have a picture on the moon. Let's see. Here's on the moon. And in the back, we have a landing rocket. You see the rocket exhaust is blowing a sheet of dust. There's a berm built here to block the dust in the direction of the outpost. There's a big curtain to block the spray. And then the mining in the front of the picture is relevant to this talk because we want to build landing pads, which means we need resources on the moon. Okay, so the overview of this talk will go like this. First, we will go over just the overview of the physics of how rockets blow soil, which is more complicated than I ever knew when I started this research. Second of all, we'll talk about why this is important, what kind of damage occurs if you don't manage this problem. Third, where do the ejecta or the blowing ejected particles, where does this ejecta go? How fast does it go? And how much of it? And the reason this is important is because you cannot land far enough away from an outpost to prevent spraying your outpost. At any distance on the moon, you will damage everything on the moon, as I will show you. And so the question is, how much are you going to damage things? And so we need to quantify how much damage will occur so that we can determine how much mitigation or how much reduction of the damage we need. And then fourthly, I'll talk about constructing landing pads. And if there's time at the end, I'll talk about an economic analysis of landing pads. Okay, so the overview of rockets blowing soil. Now, these are computer simulations of rocket exhaust. This is a side view. The rocket is up here. The exit of the rocket nozzle is at the top of each picture. And this is on the Earth, this is on Mars, and this is on the moon. The reason it's so different on the moon is because there's no atmosphere, and therefore the rocket exhaust expands very broadly. You get a large shock wave over the soil, very broad shock wave, and as a result, the pressures on the surface of the moon are spread out. So the gradient of the pressure is very small because it goes from high pressure to low pressure over a longer distance. And so when you try to put these pressures on the moon, it's like walking on snow with snowshoes. It spreads out the force, and as a result, on the moon, in all the work we've done so far, you do not dig a deep hole, whereas on the moon, on Earth, and on Mars, you do dig a deep hole, and this is why. Because of this, then the conspiracy people who say we never really landed on the moon, they'll say, well, there was no crater on the moon, and that's why. You know, this is expected. We did not expect a crater on the moon. Now, when you look at a side view, here's your rocket exhaust, here's your nozzle. This is the lunar surface, so it's a side view. In this picture, the colors mean the density of the gas. It's high density coming out of the rocket, and it's low density out here. You can see that it goes from high density to low density, but also in the vertical direction, it goes from low density back to higher density. And then this is a picture of gas velocity. So it comes out at high velocity, there's a shock wave, and then it's low velocity directly under the nozzle, but as you move out this way, it goes back to high velocity. But also in the vertical direction, it's low velocity up to high velocity. So trying to figure out how the particles get lifted by the gas, they have to travel through this boundary layer to get lifted up into the higher velocity gas. And it's very difficult to model this accurately. And so it's very difficult to predict how fast the rocket ejecta will go. Now, this is the primary mechanism that occurs on the moon. In the space literature, we call this viscous erosion, but on the Earth, we simply call it erosion. You know, in the desert, the wind blows the sand. So the gas goes from low velocity to high velocity, but the pressure of the gas can directly push particles, but also the gas has some turbulence, and the turbulence splashes the ground, which lifts particles. But especially in space, in vacuum, that gas will hit the particles and drive pressure down into the ground, which can then lift the ground, and that can contribute. So it's very complicated physics. Nobody has completely solved the physics, and so we cannot make predictions based on theory. We have to get measurements. Now the viscous erosion, because it's high pressure, low velocity in the middle, there's no erosion in the middle. The erosion takes place out here where the gas is going faster, but it doesn't take place out here because now the density is too low. So the maximum erosion occurs in a toroidal region, like a donut, around the landing point. But now there are other mechanisms that have been hypothesized, and we do see these other mechanisms in our experiments, but we don't know how much they will have a role on the moon. So one mechanism, so the first mechanism was viscous erosion, but here's the second mechanism. The idea is that this gas hits the surface of the moon and you get a high pressure region under the nozzle. Well, that high pressure drives gas into the subsurface, but because the gas traveling through the soil travels at a slower velocity and higher pressure than it does above the surface, you end up with a pressure difference. You have higher pressure under the ground than you have above the ground. And this can create regions of instability, which can cause the soil to jump up, to be pushed up by the gas and get blown away. But also when you shut the engine off, it can cause an instability. I'm going to run through that again. When you shut the engine off, then the high pressure above the ground goes away, and then it can drive the soil back up and you can get a rebound. Now, we've seen this in experiments, but we don't know if it really occurs on the moon or not, because the soil on the moon is not as permeable as sand on the Earth because of the wide particle size distribution. Now, here's a third mechanism, and we see this in experiments as well. And this mechanism they call bearing capacity failure. And that's where the high pressure of the gas shoves the ground down, mechanically shoves the soil down. And so this is similar to cone penetrometry, where you push a cone into the ground. This has been studied very much by soil mechanics experts. And when you shove a mechanical penetrator into the ground, the soil moves like this. It goes down, out, and up. It requires a very large volume of soil to move. And because it's such a large volume of soil, there's a lot of friction and a lot of resistance. And so it's hard to push things into the ground. And so this is why we do not expect this to occur on the moon, because the lunar soil is very highly frictional. But it does occur on Mars, and it does occur in experiments on the Earth. So we did a test, years ago, we did a test to find out, is bearing capacity failure really happening? So we took a box and we filled it with sand of different layers, different colors. So one color on the bottom, and then another color, and then another color. And we fired a rocket or a jet of gas. And when the experiment was done, we filled the crater with black sand, and then we filled the entire box with clear epoxy, and we hardened it, and then we cut it in half. And this is what it looks like. So here's the crater filled with black sand. But what we found was that we expected the sand to be pushed down, out, and up. But we found was the exact opposite. The soil from the bottom came up the middle. And then the next layer came up the middle around that. And then the next layer came up the middle around that. And so when we look at it, we can see there are shear planes in the soil where the soil was sliding as it was slumping and caving in. But we can see this deposits fell to the surface. So when the blast threw a lot of soil up in the air, it landed back down and created these regions. But generally, we see this kind of a motion. It goes down to the middle, up the center like this. And so this was the opposite motion from what we expected. And so this is not bearing capacity failure. So we didn't understand how could the soil move in this direction. Therefore, we created a series of experiments where we used a glass window, and we put the pipe right against the window so that we could watch the sand moving during the experiment. And so this is a video of one of the experiments. I'll show you the video in a moment. But this is the crater. The crater, it turns out, was much deeper than we expected, and it was narrow. But we looked at individual sand grains and we tracked the motion of the sand grains. And so here's the outline of the crater at this moment. And then these are the motions of the sand grains. So the sand grains were not going down like in bearing capacity failure. Instead, they're going up in a thick band. The soil was going up around the sides of the crater. Now up here, we see erosion. We see sand being lifted off the surface. And up here, we see sand being lifted off the surface and carried up out of the crater. But down here, there's no erosion taking place. It's just a thick band of soil moving uphill. And so after a lot of confusion, we finally realized what's happening. This high pressure gas is driving gas into the soil, and then the gas is moving through the soil and it's coming out right here. And so the gas is going in, traveling around and coming up, and this is dragging the soil out of the way to make the crater deeper. And so we discovered there's a new mechanism that we did not realize before, and we call this diffusion-driven shearing, or sometimes we have called it diffusion-driven flow. So it's diffusion goes into the soil, and the diffusion of gas drives the soil. Okay, so we did some simulations to study diffusion-driven flow, and so we made a very deep crater and we simulated gas blowing in. The gas goes down in, it has to come back up. So this is the Mach number, the velocity. So this is near Mach 1. So it's near the speed of sound going down in, but the gas is coming up the sides. And because the gas is going up here and it's going down here, they interfere with each other and they mix turbulently. And because they're mixing, the jet gets mixed with turbulent gas, and so the supersonic, or the core of the jet, gets narrower and narrower, and so it ends at a finite length. And so this mixing of the gas determines how far in the crater the jet can go. And so this is a picture of the pressure at the bottom of the crater, the gas pressure for 4 different size craters. And you can see when the jet can reach the bottom of the crater, you get high pressure gradients because the jet is directly touching the bottom. But when the crater is deep enough, the jet no longer reaches the bottom, and now you get a broad region of high pressure, and you no longer have a large pressure gradient to drive the gas flow in and around. And so when we look at the gas pressure, these are simulations of the gas flowing into the soil. You can see the gas is flowing in. When the crater gets bigger, the gas continues to flow in. And even when the crater is very large, the gas continues to flow in. But here you get a large gradient of pressure. And here you do not have a large gradient because it's all the same pressure. And so we calculated the forces in the sand. You get very large forces in this case, but when the crater gets too large, now you have very small forces because there's not a lot of diffusion. And so we think this is what causes the crater to grow. It's the diffusion of the gas into the soil, causing drag force in the sand, which drags the sand. But when the crater gets so long that the jet no longer reaches the bottom, then that process stops. So applying that to the moon, when you have a very large pressure gradient, a very small pressure gradient, because the plume spreads out over a wide surface, then it doesn't dig a crater. But we are worried when you have a very large rocket and it's very close to the ground, you can still have a large pressure gradient, and therefore it might dig a crater on a lunar landing. So we're still not sure if you can dig a large crater on a lunar landing with a large enough rocket. We don't know yet. Okay, so I'm going to switch to show a couple of videos here. So let me see, let me switch to the chooser, and let's see. I want to show a crater experiment. Oops, I got to open it with the other app. Okay, so here's a experiment with a high-speed camera. It slows it down, but you can see the motion of the sand getting dragged up along the sides of the crater. So this is predominantly diffusion-driven flow causing the growth of the crater. Okay, and I'll run that one more time. Mi gatto quiere entrar. Un momento. Okay. Okay, so those are some of the early experiments that we did. Let me now switch to, this is a experiment with a rocket firing into sand. Whoops. This was with a solid rocket blowing into sand. In this case, it's bearing capacity failure because it pushes the sand down. Let me show that again. You can see the layers of sand get pushed down. So this is actually bearing capacity failure. The thrust is such high pressure that it exceeds the mechanical strength of the sand and shoves it down. So we do see some cases with bearing capacity failure. We see some cases with diffusion-driven flow, and we still do not know what will occur during a lunar landing with a large enough rocket. Okay, when you look at the Apollo landings, this is from Apollo 12. It just finished landing. The astronauts got out, and they took this picture. You can see the rocket nozzle right here, and you can see there's no crater. But you can see all the evidence of erosion. You can see these little streaks in the ground, like there's a piece of gravel with a streak behind it. These are called erosional remnants. You can see this layer right here. This is a natural layer in the soil, and you can see it goes downhill as you move away from the rocket, and that's because there was more erosion out here than there was directly under, and that's because erosion gets faster farther away from the nozzle. And so we can see the evidence of the erosion, and we can see that it happened in a donut shape around the nozzle. But we don't see a deep crater. So in the Apollo landings, this scale of nozzle was not able to dig a deep hole in the ground. But we don't know what will happen with a larger rocket, and we're still working on this. And so the Apollo landing, this gradient of pressure was low enough, and the lunar soil is not very permeable. And so because of these combinations of factors, it did not dig a hole. Also, the lunar soil is very highly frictional and very cohesive. So it's very strong soil, very broad pressure gradient, and the pressure was not too high, and so it did not dig a deep hole. Okay, now we have videos of the Apollo landings. This is inside the lunar module. There's the camera. The camera was looking down and out through this window, and so we have videos of the landings. Let me see if this will run. Yes. So this is during the landing. You'll start to see the white streaks, the haziness, the dust. You'll start to see the streaks of dust. These streaks are formed around craters and around rocks. You'll start to see the shadow of the landing leg, and this is the soil contact probe shadow. Then there'll be a brief clear moment and then a big blast of sand right there, and you see the shadow moved. So look at the angle of the shadow here. And let's back up just a little bit. The angle of the shadow is a different angle here. See, the angle of the shadow is like this, but then watch the shadow is going to tilt to the left there. It tilted to the left. I'm sorry, that was Apollo 15. And the reason the shadow tilted is because when they landed, they landed on tilted ground. And so as a result, whoops, I didn't mean to get out of there. When they landed on the tilted ground, the lander tilted backwards after landing. So I'm going to break down a few of the things we see in this video. This is before the dust starts blowing. It's a clear view. Then we have this smooth flow where it's a smooth dust flow. And then we start to have streaks developing. And then we start to have more definition in these streaks. Then we have what we call the terrain modification stage. This is where it is blasting chunks of dirt, of soil, and we can, in some of the other landings, we can see solid chunks of soil blowing out, and the chunks of soil are fragmenting as they're blowing away. And finally, the landing is complete, the engine is shut off, but it stayed dusty for about 30 seconds. And we don't know why the dust stayed up in the air for so long. The dust should have cleared away within 2 or 3 seconds. So something is keeping the dust levitated for 30 seconds. And then after it finally clears, you can see it becomes clear again. We can see rocks blowing in the video. Here's a rock. We can track the rock and we can calculate the velocity. And I'll show you the velocities in a moment. We can see these things on the ground we call dust tails, where they appear for a few milliseconds and then disappear. Every time a dust tail appears, that's when a rock is being excavated by the gas, and the gas flows around the rock. It releases releases a lot of dust, and then the rock is liberated and blown away. And so you can count the number of rocks being liberated and blown during the landing. And this gives us an idea of how fast the ground is being lowered by erosion. It gives us some indication of the erosion rate. Okay, so these are the phenomena that we have seen so far. The next question is, why do we care about this? Why is this important? Well, during Apollo 12, they landed 160 meters away from the Surveyor 3 spacecraft. The Surveyor 3 had been sitting on the moon for 2.5 years. They landed near it, they walked over, and they cut pieces off and brought them back to Earth so that we could study how did the lunar environment affect all of these materials for 2.5 years. And so you see the astronaut is looking at a camera. Here's the camera. This is the bottom part of the camera. And here it is after it was brought back to Earth. This is the bottom part of the camera right here. And so they cut pieces out. They sent these pieces to different laboratories during the 1970s, and different researchers studied these materials. So around 2010, I obtained these pieces and I had them in my lab, and we have been the only group in modern times to study these pieces using modern technology. And so we were able to make a lot of progress in understanding what happened. And so here are two of the pieces that came off of the Surveyor camera. And I want to show a few features of these pieces. First of all, this is using scanning electron microscope. I'm going to show you right here. This is where there was a bolt and there was a washer, and the washer protected the paint. And so the paint is white color, but out here, the paint is tan color. So this is what the paint looks like under the washer, and this is what the paint looks like where it was exposed. And what happened was during the landing of the Apollo 12, they blew dust all over the Surveyor and sandblasted it, and it crushed the surface of the paint. So you see these rosebud shape features. These are pigment particles in the paint, but they're crushed here. And this is a crack in the paint, and there's lots of lunar dust mixed in the paint. So here we see the bolt hole. This is where the washer was. And look at this. This is a shadow. This was a shadow of the bolt. The bolt is no longer there, but the shadow is still there. And so a permanent shadow was etched onto the paint. And all of the shadows point back to the landing of the Apollo 12's lunar module. So these shadows were caused by the sandblasting of the dust during the landing. So people were wondering, why did the Surveyor turn tan? It should have been white, but now it's tan. And so they thought it was because the radiation of the space environment turned the paint tan. But what we found out, we did some electron dispersive spectrometry, where you fire electrons at the surface and you look at the spectrum of the electron energies, and this tells you the materials that are in the surface. And so this x-axis on the graph is this line right here, from the bolt hole moving across the washer, then moving across the shadow, and then moving out into the acreage. And this is the atomic percentage of 4 different elements: iron, calcium, magnesium, and titanium. Now, these 4 elements are not in the paint, but these are 4 elements that are abundant in lunar dust. And you can see in the washer, there we measured almost no quantity of those elements. And out here in the acreage, we see a significant quantity of those 4 elements. And that's because there's a lot of lunar dust mixed in the paint. But look in the shadow. The shadow has more of those elements than the acreage. And that's because the shadow, as we discovered, the shadow is actually made out of lunar dust. That means that this coloring is lunar dust. And what that tells us is that the sandblasting from the lunar landing actually removed lunar dust. So that tells us there was more dust on the Surveyor before it got sandblasted than there was after it got sandblasted. And that was a big surprise to us. And so that raised the question, well, how did all this dust get on the vehicle before the Apollo 12 even arrived? And we still don't know the answer to that. But we do know that the sandblasting scoured the surface, removed material off the surface, including removing some of the lunar dust, because the shadow, this tells us how much dust was there before the sandblasting, and this is how much dust was there after the sandblasting. And so we can see that the sandblasting scoured the surface and removed material from the surface. And in the future, that could harm hardware on the moon. We don't want to remove coatings and special surfaces. We don't want to ruin the optics of our material. Now, also, if you look over in this region, you can see the paint is cracked, lots of cracks and lots of holes, little tiny holes in the paint. So we used a laser scanner to scan this, and this is an inside out map of the surface. So everywhere it goes up, that means that there was really on the surface, it goes down. And so here we see one of these holes on the surface, and here we see one of the cracks. What we discovered is that the holes are deeper than the cracks. We also mapped all of the cracks and we counted all of the holes. It turns out that the cracks use up 22% of the area of the surface, but 66% of the holes or the pits are located on the cracks. So there's 3 times more holes on the cracks than there would have been if they were uncorrelated. So this tells us that the pits and the cracks are causally related to each other. And because the pits are deeper than the cracks, that tells us the pits caused the cracks. So what we learned is that these holes are from sand blown by the Apollo landing, penetrating the paint, and everywhere a piece of sand shot into the paint, it radiated cracks away. Not every time. This pit did not make cracks, but a lot of the pits, when they went in, they made cracks. And so the pits caused the crack. And so from this, we learned that landing near the Surveyor spacecraft caused the paint to get all cracked up because of the sand grains being blown at high velocity into the paint. And so again, this shows us the damage that can occur. Now, we counted the number of holes. We tried to quantify how many sand grains should have blown on the Surveyor based on the optical density of the blowing dust. And there should have been 1,000 times more holes than there actually were. And I will show you why we think that is in a few moments. We did experiments blowing simulated lunar soil at different materials, and you can see that lunar dust can eat a hole right through carbon fiber. This is a Kevlar carbon fiber weave, and it ate holes right through that material. And this is glass. You can see how the sandblasting of lunar dust ruins glass surfaces. And so sandblasting from a lunar landing can cause a lot of damage. And that's why it's important. We need to understand this phenomenon so that we can mitigate it and reduce the amount of damage that we will cause to our hardware. If we want to have a mining site on the moon to do mining, we have to land and leave periodically to bring people, to bring equipment, robots, and to take back the mining product. And so you have to land repeatedly at a mining site. And so we're going to need to mitigate this effect. Okay, so how far do these ejecta travel? How fast do they go? And how many particles are going to be blown? So to quantify this, we start out by measuring these shadows. In the video, you could see there were shadows of the foot pad during the landing. And it turns out that these shadows are stretched. This is the shadow of the foot pad on top of the dust. And this is the shadow of the foot pad underneath the dust on the lunar surface. And so by measuring that distance, we can quantify the angle that the dust is being blown. And so we created models. We used a piece of glass and we put smoke under the glass to measure. And then we used a lamp to simulate different angles of the sunlight. and we measured to verify that we really do see stretching of the shadows. We did computer modeling where you can see the stretching of the shadows, and we worked out the mathematics, and here's the shadow on top of the dust, here's the shadow under the dust, here's your lunar lander coming down, here's the sun angle, and so we can end up calculating the angle that the dust is being blown away from the rocket, this angle right here. And so we did the measurements. Oh, we also had to understand the geometry. Here's a lunar module that's left over in a museum. Here's the window where the camera was located. And then here's the foot pad. And so we did three-dimensional measurements on the lunar module in order to solve the geometry. And here's the result. From the 6 landings on the moon, we were able to get a measurement in all of them, except we could not get a measurement in Apollo 12. Because in Apollo 12, the sun angle was too low. The sun was too close to the horizon, so the shadows were too long. So the shadows always went beyond the field of view of the camera. And so we couldn't measure the length of the shadows. But in all the other landings, the other 5, we could measure the angle the dust was being blown. Now, in 4 of these, they all measured between 1 and 3 degrees. But in Apollo 15, they measured 7 to 12 degrees. Now, why is this? Now, remember I told you on the Apollo 15 video, at the end of the landing, you can see the shadows rotate. And that's because they landed right on the edge of a crater. As they were landing, they were going forward and coming down, and they landed right on the rim of the crater. And after the engine shut off, it rotated backwards 12 degrees. It tilted backwards 12 degrees into this crater. And so the shadows we see are from dust blowing up out of this crater. And so we're measuring this angle. And so this adds about 12 degrees into the shadows. And so that's why we measure the higher angle on these cases, but not on the others. So we generally believe that the dust should blow at about 1 to 3 degrees relative to the local terrain. And so we did computer simulations, and all the computer simulations show here's a landing rocket, here's the terrain. This simulation was done by the CFD Research Corporation under a contract that I was managing, and they took the terrain of this crater. The Apollo landed here, the Surveyor spacecraft was over here. So this is a side view of the terrain, and this is the simulation showing the blowing dust. And the dust blows at a low angle, but I have to move this little window here. Let me move this. You can see that the Surveyor was right here, and most of the dust blew over the Surveyor, missing it. And this is why we think the number of sand particles that hit the Surveyor were 1,000 times less than they would have been if the Surveyor had been in the direct spray. So the damage on the Surveyor, we think, is 1,000 times less than it would have been. And so we think the problem is actually far worse than what the Surveyor data tells us. Okay, so these are our best estimates. Computer simulations predict what velocity the particles will move, and they tell us somewhere between 1,000 and 3,000 meters per second for dust. Now, a bullet from a gun goes about 600 meters per second. So you can see these are going about 2 to 5 times faster than a bullet. The sand particles are going about the speed of a bullet. The gravel particles are only going about 30 meters per second, and the rocks, the cobbles, are going about 10 meters per second. Now, we can see the cobbles and the gravel in the videos, and we can directly measure them, and these measurements agree with our computer simulations. But these ones are very difficult to simulate. You can't see them in the videos, and they're very difficult to simulate because it's hard to model the boundary layer of the gas. And so all the different computer simulations predict different values. They vary by a factor of 10, all the different predictions. And so these are very hard to predict. And so these are partly guesses. We're guessing the velocity based on a lot of data, but we don't know for sure. Okay, so if a particle goes 1,900 meters per second at a 3-degree angle, where does it go? Well, this is an outline of the moon, and you can see these particles go all the way around the moon and then land over here. And this is the altitude of a spacecraft orbiting the moon. And so you can see the ejecta crosses the orbits of spacecraft in 4 places: 1, 2, 3, 4. And because the particles are going to go at different velocities, these crossing places are going to be in a wide variety of places. And so we have to worry about spacecraft orbiting the moon getting sandblasted. If they happen to cross that at the wrong time, they could end up getting sandblasted. And when you take into account the orbital velocity of the spacecraft, then the relative velocity on impact exceeds 4,000 meters per second, which means these are hypervelocity impacts. What that means is that the particles hitting the spacecraft will impact at greater than the speed of sound in the target material. So when an impact hits a material at greater than the speed of sound of the target material, you get a shock wave in the target, and you get vaporization of some of the target material. And so it causes a lot more damage. So we have to worry about orbital spacecraft being damaged by lunar landings as well. So here's a simulation where this is the outline of the moon, very dim, I apologize for that, but it lands right here, and you can see the ejecta being blown out. And so I'm going to run this video. It takes about an hour for the ejecta to go all the way around, so you can see this has been sped up a lot. So this is what the ejecta looks like when it goes out. It blows out, it goes all the way around the moon, and then it continues to land on the moon for days, many, many days, because some of the ejecta goes very close to orbital escape velocity, and so it takes a long time to come back down again and land. Now, this simulation does not take into account the motion of the moon around the Earth, or the motion of the Earth-Moon system around the sun. So we don't expect that the ejecta will keep hitting at the same location, but this is just to give the general idea. So this is, now I'm going to show you, here's the moon, and this is the orbit of the planned lunar orbital gateway, which the international community is planning to build around the moon. And it's in a very elliptical orbit. It's called a near rectilinear halo orbit. This is the moon, and you can see the ejecta starting to blow off the moon. So here's the ejecta, and you can see it crosses the orbit of the space station that we plan to build around the moon. Now, the space station has an orbital period of about 1 week, or I should say it is planned to have an orbital period of about a week. And so depending on how rapidly the dust disperses, it may fly through that ejecta sheet multiple times. Now, this orbital velocity is very slow. It's only a few hundred meters per second. And the dust, by the time it gets this high from the moon, the dust is also traveling very slow. So these are no longer going to be hypervelocity impacts, and it will not cause that much damage. But it will cause some damage, a small amount of damage. We don't need to worry about it too much, but we do need to remember that to take this into account when we plan sensitive instruments on the gateway. Okay, so how much dust is going to blow? We've done a lot of experiments to try to quantify it. That's me inside of an airplane doing reduced gravity experiments of blowing soil in a small experiment. This is one of the videos I just showed you. We've done a lot of terrestrial experiments. We went to a volcano and we fired rockets on the volcanic ash to study the blowing dust. These are some of the analyses of our experiments. This is an experiment inside of a giant vacuum chamber where we had 10 experiments set up inside of a giant vacuum chamber. And this is firing motors, solid rocket motors, into sand beds. So the end result of all of our experiments tells us when you are in Earth's atmosphere, when you are in a thick atmosphere, you get this result. So the rate that the volume of the crater will increase. So the velocity, the derivative of the volume of the crater with respect to time is some proportionality constant times this ratio. The numerator is all gas parameters. The denominator is all soil parameters. So this is the density of the gas times the velocity of the gas squared times the area of the jet, the exit area of the pipe. So this is the momentum flux into the experiment. The denominator is the density of the gas, the density of the minerals times the gravity times the diameter of the sand grain, and we think plus cohesion. Because when you get to low gravity and this term becomes less significant, we can see that this is no longer accurate. We don't know for sure, but we think there probably needs to be a plus cohesion term, but we don't know really what this term should be. But in any case, because these are all soil parameters and gravity, these are all parameters of the environment. And these are all parameters of the rocket in the numerator. And therefore, we can separate it. Now, in some cases, this numerator is proportional to the shear stress that the gas places on the soil. So for an approximation, we could say that this is the shear stress of the gas times a collection of terms which represent the environment. And because on the moon, the soil is kind of similar most places, we can treat this whole term as a constant. So we got the idea, let's measure this constant from the Apollo landings. And then we can, for any given rocket, we can calculate the shear stress by simulating the gas. So we tried to do this. So in these landings, we measured the optical density of the dust. Here's a rock. And then here's the same rock where there's a gap in the dust. And so by measuring the bright and the dark on both sides of the rock, both with and without dust, we can calculate how much dust there is. And we've done that, but it's not very accurate. And there's a lot of parameters that we had to make assumptions. So when we vary all of the different parameters over 648 different cases, we can predict how much soil was blown. And the predictions are over a wide variety, a wide range of estimates. So all the way from 80 tons of soil, all the way down to 3.5 tons. This is not a very accurate method, but the average of all of the parameters, when we vary the parameters over all the different possible ranges, the average prediction is almost 20 tons of soil were blown during each lunar landing. Now, we think that this is wrong, because when we look at the pictures under the lunar landing, it looks like maybe about 2 tons was blown. When we look at the height of these lips of soil and other features, we crudely estimate it should have been about 2 tons. So this method is off by about a factor of 10, we think. So it's not very accurate. It's because there's too many assumptions, too many guesses in all of the parameters. Furthermore, we did experiments in a vacuum chamber, and when this is the Knudsen number, meaning this is a measurement of how rarefied the gas is. When the Knudsen number is low, this means it's very dense gas. So we maintain the numerator of that equation constant. So when the density of the gas goes down, we raise the velocity higher to keep this term equal to 180.7 pascals. And what we find is that when the gas is dense, you get less erosion, and when the gas is lower density, you get high erosion. Now, this disagrees with all of our experiments that we did in Earth's atmosphere. In Earth's atmosphere, when we keep the density of the gas constant and change the velocity, when we keep this term constant, then the erosion is constant. But once we start to go into a rarefied regime, when we start to get the gas so rarefied that the Navier-Stokes equation is no longer valid, the erosion actually gets faster. And so this tells us that this equation is probably only valid when the gas is dense enough so that Navier-Stokes equation applies to it. But when you go to lunar conditions, this equation no longer works. And unfortunately, we don't have enough data to really measure what the equation should be when it's near vacuum conditions. When we plotted all of our data from our vacuum tests, they scattered all over the place. When we tried to normalize it by that equation, it did not cause the data to collapse. And so unfortunately, we weren't able to figure out a new equation. When we take a subset of the data using only one kind of sand, then the data collapses partially. It's still very noisy data, but at least we can see the trend. So when you are in continuum conditions, it's fairly constant. But when you start to go to vacuum conditions, we can see the erosion rate gets faster. So we tried one more method. We look at these images of the landing, and we can do synthetic. We can synthetically add dust to the image, because we know what dust does to the propagation of light. So we did some video manipulation where we added synthetic dust to make the video look hazier. We can also subtract dust to make the video look less hazy. So here's one where we took this image, we subtracted dust to try to make it look sharper like this image. Or we can do it the other way. We took a sharp image and we can add dust to try to make it look hazy to match this image. And then we can say, how much dust did we have to add to the image to make it match? And by doing that, we can try to estimate how much dust is in each picture. When we do that, we plot the, I don't have time to go through all the details, but when we do this at different points during the landing, we can end up with an equation. And this equation says that the rate that the mass is being eroded is equal to shear stress to the 2.5 power. Now, as you recall in our previous equation, it was shear stress to the unity, shear stress to the 1. This is saying shear stress to the 2.5. Now, unfortunately, I think that this is wrong too. We have more recent data that says that this is wrong. So what I want to say for our conclusion is we just don't know. Everything we've done for 20-something years and we still don't know. But we do think that something changes when a lander is descending toward the moon. It goes from very high down to very low. The Knudsen number, you know, the measurement of how rarefied the gas is, that Knudsen number decreases. You eventually get into continuum flow. If it's a larger lander, you get more deeply in continuum flow. And so we think that something transitions, but we don't really know the equations yet. But our best estimate so far is that about 2.6 tons of soil were blown during the Apollo landings. When we use that equation with the 2.5 power index to the Chinese lander, it predicts only 20 kilograms of soil would blow. But when a research team in China applied the same method that we developed, where you synthetically add or subtract dust, they measured 200 kilograms of soil. So our 2.5 power index is off by a factor of 10. And so that's why we think we still don't have the right equation. So we still don't have an equation to make predictions. Also, if you do start to erode the soil, the properties of the soil change as you erode the top layers. Nobody has ever done any work on this yet, so we just cannot make good predictions. If you dig a hole on the moon during a landing, it will change the, if the crater itself forms under the landing, the crater will also change the angles that the dust will blow. We have tried to estimate how much ejecta gets blown different distances for different size landers. I don't really have time to go through the details. We do have one data point from the Surveyor lander. That was a 5-ton lander, so it's more thrust than these cases, and that seems to be about right. Where that dot falls, we measured the amount of eroded, the amount of impacts on that Surveyor. And so by using these data, we can try to estimate how much damage will occur at different distances, but it is a very crude estimate. When you look at the different mass vehicles, a larger vehicle will blow more gas, and therefore we can try to estimate the velocity of the dust for different size particles. Larger vehicle will make the dust go faster. It increases as a logarithmic function, we think. Also, if your rocket uses different rocket exhaust, if you use kerosene like in Apollo, the maximum velocity is 3.1 kilometers per second. But if you use methane or if you use hydrogen, the dust can blow faster. So we have very crude guesses at the speed of the particles as a function of the particle size, the mass of the vehicle. Here's lunar escape velocity. We think particles above about 10 microns can be blown completely off the moon, but these are very crude guesses. We really just don't know. But using these crude guesses, we can estimate how far do you need to land away from your landing site, from your outpost, to get the damage below an acceptable level. We say, well, the Surveyor damage was too much damage. Maybe 1% of that damage is acceptable. But if you want to have 20 landings, then you need to reduce it by another factor of 20. So you need to reduce it from here down to here. But if you use a larger lander, it's going to be starting from even larger. So you need to reduce it from here all the way to here. And so how far away do you need to land? And that predicts 26 kilometers away. So 26 kilometers is your landing distance, and that's too far. You can't land and then walk 26 kilometers. And so that means you need to build a landing pad. And so final part of this talk, I want to go through landing pads. How am I doing on time? Do I need to speed up to get through this real rapidly, or do you want me to continue like I'm doing?
I will say that I am enjoying it so much that I will let you extend your presentation as much as you want.
Okay.
Okay. As we are recording, if someone else needs to leave, is free to do it. And if you have time, please go forward.
Okay. All right. Well, I don't have too much more, but thank you for explaining. I will go through the rest of the talk then. Okay. So this is our best estimate. If you have a 40-ton lunar lander, using some modeling, we can predict how wide is the region where the gases will be hot. We added 5 meters for landing accuracy. This is assuming a multi-engine lander, so the multiple rockets some distance away from the center. And so we estimate 12 meters for your inner landing zone, which has to handle the high temperatures of your rocket exhaust. Outside of that 12 meters, you no longer need to worry about the high temperature, but you do need to stop erosion. And so this 27 meters is, again, it's based on the 5-meter landing accuracy, but using very crude estimates as best as we can do today, we think at this radius, nothing out here will be blown by the rocket exhaust. So that tells us for a 40-ton lander, we're thinking about 27-meter radius for a landing pad. Now that's a very large landing pad. That's a large quantity of material. And so the economics of building the landing pad become very important. We've looked at different methods of building landing pads on the moon. Every different method starts with site preparation, grading the surface to make it flat, removing boulders. How do you remove a boulder? Well, you dig a hole next to it and then you push the boulder in the hole and then you cover it over. That would be an easy way to do it. Or you pick a different spot. If there's a big boulder in the way, you just move somewhere else because it may be too hard to move the boulders. And then after you grade the surface, then you compact the surface. Now this is important because some of the methods of building landing pads, you're going to be laying bricks or you're going to be sintering, and the process control is very important. And so you need a very level surface. So grading and so site preparation is very important. Now there's been a lot of experiments. These are rovers from Canada doing bulldozing tests. And this is a rover from NASA doing a bulldozing test. Now on the moon, you can use operators on the Earth controlling the robots because the round trip time delay is only about 3 seconds. But if you want to build a landing pad on Mars, it might be a 20-minute round trip time delay. So you need artificial intelligence to control your robots. Even on the moon with a 3-second round trip time delay, it's very difficult to control a machine. And it becomes very inefficient to have humans in the loop with that much time delay. So we think we need to have a lot more artificial intelligence to make this a more automated process. Okay, so I've done some modeling of how much energy it takes to push a blade, to do grading and compacting. I've put all of this into a spreadsheet, including some guesses. But we've tried to quantify this based on data as best as we can. And so I will show you the results of this modeling in a few moments. Now, the next thing is after you've done site preparation, you need to create a competent surface. And we have looked at different methods, including solar sintering. Now, the problem with solar sintering is that the energy in the sunlight is primarily in the visible wavelengths. And the visible wavelengths do not penetrate soil very far. And so when you try to do sintering, it only creates a thin crust of material. And see, we blew a small thruster on, we built a small surface with solar sintering and we blew a small thruster on it and it just crumbled it and blew away the landing pad, destroyed the landing pad. So optical sintering is not very good unless you additively continue adding material to build up a thick surface. But we haven't had enough study yet to determine whether you can build a surface that will resist delamination of the layers once the rocket exhaust starts to blow into those layers and penetrate the material. So there needs to be more work to determine if solar sintering will be good for landing pads or not. We've also done some work with infrared sintering where you use something like a toaster oven to make toast. I don't know if in Spain if you have toasters like in the United States, but it's just a resistive heating coil that gets red hot, and the infrared radiation then radiates away from this resistive heating element. And again, at infrared wavelengths, the optical the wavelengths do not penetrate the soil very far, and so you have to additively build up layers. Well, when the process is difficult to control, and we did not get good bonding between the layers, and so when we fired a rocket thruster onto it, it delaminated the layers and it crumbled the landing pad, and so it did not build a good landing pad. But this, you can see the red glowing heat from trying to build a landing pad on volcanic ash using this machine. So it did not work very well. It needs more improvement. Now, microwaves, the nice thing about microwaves is that they have a very long wavelength and they penetrate the soil at approximately the correct depth so that you can build a landing pad of the right thickness in a single pass. And so microwave sintering is much easier, and it's already pretty mature. I mean, it needs a lot more work, but we've already been able to build thick materials that are several centimeters thick enough to be a landing pad. And so I've done modeling of microwave sintering. How much energy do you need to build a landing pad? How much time does it take? And I will show you the results of the modeling in a moment. Another method is pavers. You can make pavers in an oven. You can put lunar soil into a mold. You can bake them using any method to heat the paver and then let it cool. And then you take the pavers out and you can make a landing pad. Now, this was done in Hawaii. This rover from Canada and a robotic arm from Honeybee Robotics. And these pavers were built by the NASA Swamp Works. And you can see these are interlocking, so they hold each other down. And so they built a paver, they built a landing pad. Now, the problem with this is that the gas in experiments that I did earlier with Paul Van Susante, the problem is the gas goes through the cracks and it builds up pressure under the landing pad. And you can actually build up more pressure under the landing pad than the pressure coming down from the rocket. And you can actually explode the entire landing pad. Now, when they did this test, they fired the rocket right on the center of one of these pavers, but the thermal expansion from the rocket cracked the material. The gas went through the crack. It inflated the bottom of the landing pad with high pressure gas, and the entire landing pad exploded. And so this shows that using pavers has problems. Even sintering, it can be a problem if you don't resist the thermal expansion, and if you form cracks and you get gas under your landing pad, it can be a problem. But so the problem with pavers is we think you need to grout the cracks to keep the gas from going through, and the grouting turns out to be the most lengthy part of the construction process. And so grouting needs more technology work. But I've done modeling in the spreadsheet of making bricks in an oven using examples from terrestrial industry. I've tried to quantify it, and I'll show you those results in a minute. And so another method of building a landing pad is you can use rocks from the moon. Now, you can't do this for the central landing zone. So in the middle of the landing pad, you have to have a material that will keep the gas from going through. But you can use this for the outer part of the landing pad. And the rocks are already on the moon. So Paul Van Susante, originally from Holland, the Netherlands, he's now at Michigan Tech in the United States. He innovated this method, and he used a rock rake to go around and rake the soil to collect rocks of different sizes, and then you lay them down, small rocks first, and then larger rocks, and then larger rocks. And the idea is you want to have the rocks on top large enough to hold down the next size rock. And then this rock holds down the next size, and then the gas has to go through all of these layers, which slows down the gas, so that by the time the gas gets to the bottom, it's not able to lift the dust. And so Paul innovated this method, and I've done some modeling based on rock sorting devices, based on experiments that we've done here on the Earth in rock sorting, and I put that into the spreadsheet. So the final method that we've studied is using polymer. You can simply spread polymer on the ground. Now, this is problematic for the central region on the landing pad because polymer breaks down at high temperature. And we've done tests with polymer. These tests were done by Michael Hogue and Rob Mueller of NASA, where they blew superheated thin air at lunar soil that was filled with polymer. And they studied how does it ablate and wear out. And so if you use a high temperature polymer at maybe 15% weight of the soil mixed into the soil, then it could withstand a landing in the central part of the landing pad, but it will still ablate. And so you may need to do periodic repairs or replacement of your landing pad. And so we don't know enough about this yet. So in my study, I've assumed that you're only going to use polymer for the outer part of the landing pad. And we think maybe 5 weight% might be enough. Maybe that's not enough polymer, but this is what I've assumed in my study. Okay, so also you could make polymer on the moon using the lunar ice. We know that the lunar ice contains hydrogen, carbon, and nitrogen, so you could make different plastics on the moon. But that will be in the future when we have more industry on the moon. So for now, you have to bring the polymer from the Earth. And that's a lot of mass you have to bring from the Earth. But it is a very easy and very rapid method of building a landing pad. So here's the data in my spreadsheet. So this is the result of my trade study. In the inner region, you can use sintering or pavers or high temperature polymer. I did include the high temperature polymer at first in my study, but in my later study, I no longer consider this. But then for the outer pad, you can use sintering with microwaves, or you can use pavers, or you can use polymer, or you can use the gravel that you've raked from the moon. And so each method, you can predict how many days it takes to build the landing pad. And you can see anywhere from 1 day for the outer pad, or all the way up to 87 days. And then it predicts how much energy you need, all the way from very, very little energy for polymer, all the way up to gigantic amounts of energy to do pavers or sintering. And then how much material do you need to bring from Earth? The consumable materials like polymer, 20 tons of polymer, that's a lot. And how much equipment you have to bring from Earth. And you can see microwaving requires more equipment than the other methods because you have to apply the microwaves at a high rate. And so when you put this all together, you can make a plot that shows construction days compared to the mass you bring from the Earth. And you can show construction days versus the energy you need. And so we don't really know which is the best. You know, is it better to have fewer days but more mass? Or is it better to have fewer days but more energy? We don't really know, but we think maybe some of these in the middle are the best. So maybe using pavers on the middle and gravel on the outside might be the best. That's number 7. Or maybe sintering the middle with polymer on the outside. So we thought maybe one of these would be the best method for now until there's more technology development. But more recently, this is work I have not published yet. I've done a preliminary presentation once on some of this, but I'm going to show you new results that I just wrote into a paper, and it has not yet been published. So in order to combine all of these together, we decided let's do an economic analysis, because you can quantify the cost of a construction delay, and you can quantify the cost of bringing equipment and mass from Earth, and you can quantify the cost of energy. So we can quantify everything in terms of economics. So to do that quantification, we said, well, how much does it cost to build an outpost on the moon? And we just said $130 billion US dollars based on the space station. This is not really what we think it will cost to build on the moon, but what we said was the international community was willing to spend $130 billion. So this gauges the amount that the community is willing to spend. So let's just start with that number. But then the value of the lunar program is important to quantify, because when we want to say what is the cost of a delay, the cost of delay is based on how much you're delaying the value. And the value is typically more than the expense that you paid. You know, if you pay $1 for something, you expect to get more than $1 of value. So this is 1-to-1 value to cost, 130 billion, or you could say 4-to-1. Let's say we expect 4 times the value, or this is 20-to-1. Now, for a 20-year program on the moon, if you get 10-to-1 value per 10-to-1 for the first decade, and then another 10-to-1 for the second decade, 10 times 10 is 100 times the value. So even if we say 20 times the value, we think that's still pretty conservative. You know, the value of the moon is so high, in our opinion, extending industry and civilization to the moon is so high that we think even 20-to-1 is a conservative estimate. But we said, let's use 4-to-1 as our baseline estimate of the value of a lunar outpost. Now, there's also an operational annual operating budget for the space station. It was $3 billion per year, but we're not going to include that. So these are our estimates of the value of the program. 20 years on the moon at that value. You can use the equal payment present value formula to calculate what is the present value of your lunar outpost, of your lunar program. And then every year that you delay it, if you assume a 3.5% rate, this is the a pretty common rate you could use for in the United States for the discount rate of federal money. So at that discount rate, you can calculate the present value of the lunar outpost and then calculate the cost of delaying the value. But if you have a 1-year delay, it's not going to delay the entire program. It's only going to delay some of the activities. And you can work around and continue to do other activities. So we surveyed a lot of program managers, and they said, optimistically, the best you can do is continue to work 75% of your program, and probably at the very minimum, 25% of your program will be delayed when you have one long item like a landing pad. And so we're trying to be very conservative. So we said, let's optimistically assume that 75% of the value will not be delayed. Only 25% of the value will be delayed. So these are the numbers we use to calculate the value of, or the magnitude of the cost of delay from building a landing pad. To develop the hardware, we used an online cost estimating tool for spaceflight hardware. It crudely estimates $1.7 million US per kilogram of spaceflight hardware. Transportation cost to the moon is currently about $1 million per kilogram, but we said, well, maybe by the time we start building a lunar outpost, it will come down by a factor of 3 to about $300,000 per kilogram. But we do vary these parameters over a wide range. And we also estimate that yearly operations cost. I forgot, I'll be honest, I forgot what this number is. Yearly operations cost for pod construction. I forgot this, but it doesn't actually come into the calculations. I'll have to go back and look at my paper. I copied this chart from another presentation, and I forgot how I calculated that number, but it doesn't come into the calculations anyways. Okay, and then energy cost, we can base it on solar energy. Current technology, it's about 30 kilograms of solar cells to get a kilowatt of energy. And if the solar cells have a lifespan of 20 years on the moon, then we can calculate at the transportation cost, we can calculate the cost per kilowatt hour to the moon. And also there's a duty cycle. If you're on the equator of the moon, it's 50% night, 50% sunlight. But if you're on the poles of the moon, there are places where you can get 80% sunlight if you have a solar cell that rotates to follow the sun. Okay, so the reliability of the different technologies. If the inner pad is sintering and the outer pad is sintering, I went through a reliability engineering analysis, and we came up with very crude reliability estimates. The paver method has the lowest reliability because all of the robotics to fill the molds with lunar soil and to remove the pavers from the oven and put them on a rover, all of that robotics operating in lunar dust has low reliability. So if you try to build the inner and the outer pad, both from pavers, then it's very low reliability. So this is sintering, sinter gravel, sinter paver, sinter polymer, or the inner pad can be paver with each of the 4 types of outer pads. But then you can go through your reliability cost engineering using the minimum cost to improve each method and come up with a cost factor to get everything up to 99% reliability. And it turns out that reliability is not a strong driver of the economics, because for only 50% additional hardware cost, you can achieve additional reliability. Well, 50% hardware cost sounds like a lot, but it turns out hardware cost is not the real cost driver on the moon. So when you look at these 8 different optimized construction methods, these bar charts show all the costs. Delay cost, which is a dominant cost. Operations cost is so small you can't even see it. Energy cost is so small you can't even see it. It's right in there. Transportation cost is a dominant cost. And then hardware development cost is so small, it's down here, you can't even see it. So everything is dominated by transportation and cost of delay. Now this is for a non-optimized set of hardware. But it turns out if you use a larger set of hardware, which uses energy at a faster rate, then you can build the landing pad faster, so your delay cost goes down, but your other costs go up, and then there's an optimized point, and then beyond that point, you're no longer decreasing your delay cost as much, but you're increasing your energy and your hardware and your transportation cost. So there's a minimum, it turns out, for the quantity of equipment to build each construction method, and the optimum point for each construction method is in a different location. And so if you assume that you optimize every hardware set, this is what the costs look like non-optimized, and this is what they look like after you've optimized everything. And you can see this method here costs about $4 billion, but now it only costs about $3 billion. So we've reduced 25% of the cost by optimizing your hardware. Now, I know that these are all very crude estimates, but the purpose of the study is just to find out, is there really one good construction method that's very much better than all the others? And it turns out that they're all kind of similar. They're close enough that if you have an advancement in your technology, then you can make one of these other methods better than the others. And so right now, sintering seems to be the best, but sinter paver is pretty close. And even sinter gravel is not too far. And even sinter polymer is really not too far. So there's no great winner right now for the inner pad. For the outer pad, I'm sorry. So the outer pad, polymer, I'm sorry, let me just go on. I'm getting myself confused. So now all of this was based, and I'm almost done here, but all of this is based on an economic scenario. And so if you have a higher delay cost or a lower delay cost or no delay cost, you get different results. Likewise, if you have a higher transportation cost or a moderate transportation cost or a very low transportation cost, again, you get different results. And the trends show us that, let's say that you've got expensive transportation, as you go to less and less delay cost, then the polymer is less competitive. And that's because the primary benefit of polymer is speed. But in polymer, a large fraction of the cost is transportation of the polymer from the earth. And so if the delay cost is high, then polymer is more competitive. But if the delay cost is low, if you don't care how long it takes to build your pad, then polymer becomes more competitive. Likewise, if you change your transportation cost, so let's look at this. If you have a low delay cost, this is kind of a moderate delay cost, but it's lower than our baseline, then polymer is not competitive. But if you go to lower transportation costs, then polymer becomes the best method of building the landing pad. So it really depends on your economic assumptions. Now, if you use our baseline economic scenario, but you vary the transportation cost, then it turns out sintering the inner pad, sintering the outer pad is the cheapest method of building a landing pad until the transportation costs get below about $79,000 per kilogram. Now, we actually think that this is going to happen in about 10 years. Once, if SpaceX is successful with their very large lunar lander, if Blue Origin is successful with their large lunar lander, if other companies and other entities are successful with their landers, and if a lot of economic activity is happening in space, then the launch rate will be higher, the landing on the moon will be higher rate. We think that these costs in about 10 or more years will come down to this level. And so there is a crossover where sintering the inner pad, polymer for the outer pad, then becomes the cheaper method according to the current estimates. So using our baseline economic scenario with a 4-time expected value for the delay cost at 4 different transportation estimates, sintering is the most economic at current costs. You would need, for the optimized system, you would have 2 lunar rovers. The total mass of your rovers is about 440 kilograms. The total mass of your sintering hardware for microwaves is 1.5 tons of hardware. You won't bring any polymer. You'll need about 82 kilowatts of power on the moon. That's a lot of power, but you can do that. It'll take about 46 days to build a landing pad. The total cost, including delay cost, is $4 billion US. But the real cost that you show on your budget, not counting the delay cost, is going to be about $2 billion. That's still very high, but it's less than 2% of the cost that we expect for the lunar outpost. If the transportation costs go down to $100,000 per kilogram, then it's optimum to use 7 lunar rovers, and you'll have 4.5 tons of sintering hardware, because you can send more hardware to build the landing pad faster. And so now it takes less than 15 days to build the landing pad, but you need about 260 kilowatts. Again, you can do that. You can bring enough solar energy to do that. The total cost, including the cost of delay and energy cost and everything, has come down from 4 billion down to 1.4 billion. Even though you sent more hardware, it's overall cheaper. You're recovering more value. And your budgeted cost, the budgeted cost does not include the cost of energy, does not include the delay cost, because those are going to show up on a different line item for your outpost budget. But your total cost on the budget for the landing pad is now under 700 million US dollars. And so the politicians will find that to be a much more acceptable number, and because it's less than $1 billion. But you can see that as the cost of transportation comes down, it'll become more economically viable. Now, these are still very large numbers. And I think that there's some reality we can put into this to reduce those numbers even further. Now, it turns out that if you build the landing pad faster and faster, you're not really going to recover all of that delay cost. Because if you build your landing pad in 1 minute instead of building it in 10 minutes, that extra 9 minutes is not going to help anything, because everything else going on the moon also has a schedule, and you have a launch rate, and you're not going to have launches to the moon every 5 minutes. So you can't really recover all of your delay cost. And so taking into political reality that you're going to have a fixed launch rate to the moon, what if we just crudely say you can only recover about 1/6 of your delay cost? Well, now your optimized hardware set is only 1 lunar rover, and your budget comes down. It was going to be $2 billion. It now comes down to $1 billion. But it takes a lot longer. Instead of building a landing pad at 46 days, it now builds a landing pad in 110 days. But that might be optimum because it depends on how often you launch to the moon. If you're only going to launch to the moon a couple times a year, then 110 days might be perfectly optimum. And so it may be that we can get the cost down to $1 billion, even at the current launch prices. But for $300,000 per kilogram, it gets below $500 million. And then another economic reality is we think that as the cost of transportation goes down, although the value of doing things on the moon is still high, the cost of doing things is going to come way down. And so I crudely estimated that when the cost of transportation comes below $100,000 per kilogram, then the cost of building the outpost scales with the transportation. And so the cost comes way down. And so in those cases, the cost of building a landing pad comes down to less than $50 million. And so maybe in 20 or 30 years from now, building a landing pad on the moon will be the same cost as building a large building here on the Earth. And so it starts to become very reasonable. So anyways, that is my economic assessment of building landing pads using current technologies. As I mentioned before, these are actually pretty close in cost. There's no clear winner right now, in my opinion. Excuse me. And so if you can dramatically improve one of these methods or another method, then you may end up inventing a method that is better than all of these. And so at this point, I recommend that we continue investing in all of the different methods, because we still don't know what is the very best method to build a landing pad. Okay, so that was the talk that I had, and I'll be glad to answer questions if anybody has any questions.
So thank you very much, Phil. Has been fantastic. It's much more what I could possibly expect for this presentation. It's quite comprehensive, everything since the necessity till the economic value at the end. And I still have in my mind the image of the pavers blowing. This is nice thinking, okay. And also I want to let you know that yes, we have toasters too, and in the same way as yours. So we know what you're talking about regarding that thing. At least it has been very easy to follow you. And I have a few questions for you, but lest the people ask if they want at this point. Anyone else have a question? We usually raise digitally our hand who have questions. So you have been talking for so long, Phil, that your throat must be painful. I'm sorry about that. So if nobody else want to break the ice, I will be the first one. And I have many questions, but there is always one thing that crosses my mind when I see this kind of presentation. And probably you know a lot because you are researching in this field. And probably my question is going to be bad formulated, but please humor me and try to answer. And always when we talk about a permanent settlement, settling the moon, we're always thinking in small, let's say, houses over the ground. But in my mind, I don't know why, probably because I have strong ties with mining engineers, I always think that this would be better to construct our settlements under the ground, protected for extreme temperatures, for radiation, for micro impacts, whoever cross your mind. But I always thought that probably the question probably the answer to that question that nobody else is thinking about that is because you need to move a lot of huge equipment. But after hearing your talk, I am being able to understand that you are also planning to move a lot of equipment, and you are also planning to, or the community is also planning to exploit the mining and mine the moon. So why nobody is wondering, or maybe they are and I am just ignorant, doing permanent settlements under the soil, under the ground? My question is why, because I have not been able to find many papers related to that.
Well, there have been people talking about this. So a lot of the studies that have been done by the space agencies like NASA and the European Space Agency, they're focused more on the near term. And so they assume that we are constrained by the cost of sending equipment to the moon. So they try to come up with methods to build on the surface. And we do want to go under a lot of mass because the radiation on the moon is very bad. Here on the Earth, we have a nice thick atmosphere. That atmosphere protects us from cosmic radiation, and it's equivalent to about 10 meters of Earth. So the radiation at the surface level of Earth is the same as if you were on the moon 10 meters underground.
Precisely.
Right. And our bodies are not adapted to such a high radiation level. But the problem is it does take a lot of equipment, but there's another technical problem. The moon does not have plate tectonics the way the Earth does. It does not have active volcanism. And there is no resurfacing of the surface over geological timescales. And because of this, the entire surface is fragmented into regolith to a depth of about 10 meters. And even below the 10 meters, then we call it the mega regolith, where it's still highly fractured, but it's very blocky, boulders. And you have to go very deep before you get to real competent bedrock. And so one problem would be developing the technologies to stabilize your mining shafts as you're digging into the ground. Of course, we have a lot of, I don't know much about that field, but I know that already here on the Earth, you're very used to digging into fractured materials and stabilizing it. But on the moon, we think the fracturing is even more than on the Earth. And so, so you will need to plan on a lot of stabilization as you dig. Also, the moon does have strong quakes. We have only about, I don't know, a few years of data. During the Apollo program, they put several seismic sensors on different parts of the moon, and we have several years of seismic data. And we can see that there are a power spectrum of quakes on the moon. When you extrapolate that power spectrum out to 100 years, then you can calculate the probability of a very large quake happening. So the kind of earthquake that here on the Earth would destroy a whole city, it can occur on the moon in about 100-year time scale. Now that's at one place on the moon every 100 years. So the probability might still be pretty low, but nevertheless, we do need to consider that you need to stabilize for moonquakes. So with those conditions, there are two main ways that people think about this. Number one is they talk about building on the surface, but pile up the soil on top of your outpost. So it's a lot of earth moving, but you can pile it up. So the European Space Agency has some very nice pictures of a proposed lunar outpost, and that's what they have demonstrated. They have shown piling up soils many meters deep on top of the outpost. The other method people talk about a lot is finding a lava tube, because we know the moon does have lava tubes. And some of these lava tubes, the ceiling has collapsed to make skylights. And we can see these lava tube skylights from orbit. And so people talk about finding a nice large lava tube that has stable ceiling, and you can go down in there and build your outpost inside the lava tube. There's very serious study about this concept. People are very serious about it. So these are a couple of the approaches people are talking about seriously. Now, I do know other people who talk about excavating underground mines on the moon, stabilizing it as you go, and just like we do here on the Earth, building vast caverns under the ground by mining. So that's also a possibility. Now, to do that approach, that assumes that the transportation costs will come down. We will send a lot of equipment. We will build up the industry. We will get economic value. So that will justify sending more equipment and building up the industry. I do believe that will happen. And so one of my best friends is an advocate of that approach. So there are people who talk about doing that, but I have not seen much of the engineering to do that. I have not seen any of the engineering, but there are people who talk about it.
So I knew about earthquakes and lava tubes in Mars, but I was not expecting the same in the moon. I thought like it was a big stone and nothing else. So thank you very much.
The thing about the moon is that it has some very large impact basins, and those the rock around the rims of those basins is not stable.
I see.
And so you get quakes over long time periods as it continues to settle. Even billions of years after these basins were formed, they do continue to have periodic quakes. Now the moon is rocking because of tidal forces with the Earth. And so we do see deep mantle quakes with a periodicity based on the rocking motion of the moon, based on the month of its orbit around the Earth. And so there are dynamical drivers that continue to affect the mantle on the crust of the moon.
I see. When you talk about billions, you are thinking in thousands of millions.
Yes,
isn't it?
yes. I know.
Okay.
I know in the United Kingdom, a billion is a million million. I don't know about
That's
Spain.
right.
Here in the United
Yeah.
States, a billion is 1,000 million.
Yeah. I think it's everywhere else except the United States. A billion is a million of millions, but
Oh, really?
it's okay.
Okay. Thank you.
Yeah, I think so. I think so.
I want to update all of my charts in the future to be more clear about.
That only means that you are exceptional, no? In another in another way. So for my part, I have so many questions. It's quite interesting that being able to realize that someone is thinking not only in the engineering and in the different technical possibilities, but also thinking how much it's going to cost, how much is going to delay, how much that money is going to get back, no, to the investment, and it's really nice to know that. So I don't know. Everybody else want to ask something to Phil. It's quite an opportunity to have someone like him here with us. Probably people is tired to hear me, not you, because you was quite interesting. So Phil, I have your email. Thank you very much again. I need to process all this information because I have a few more questions. We have been working in some techniques for consolidation of soil here, but I am not sure, but I am thinking that all of them need oxygen, so probably are of no use, at least at this point. But one last question, now that I'm thinking, when do you think this could become a reality? When the first settlement, when the necessity of landing pads will arise and we will begin to exploit the moon, let's say?
So, so NASA and the international community are planning to return humans to the moon and to build a space station around the moon and to begin landing humans on the moon and doing surface operations within just a few years. So we hope that the first human landing will be in just a few years. I don't know the exact schedule, but maybe 5 years.
Oh, that's nice.
And so this is we're talking about very, I'm sorry, my throat is hurting.
No, yeah.
About very large landers on the moon. Now, the first landing on the moon, you don't care about sandblasting too much because there's nothing else there to damage except the historic artifacts. You know, as long as you land far enough away from the historic artifacts, that should be okay. But if you want to build an outpost, the second landing is the one you worry about, because the second one is going to sandblast everything that you landed on the first landing. So we think we need to start building a landing pad on the first landing. That way the second landing has somewhere to land. Now, as far as I know, I'm no longer with NASA. I'm with a university. So I don't know the official plans. But as far as I know, nobody has committed to the idea of building a landing pad yet. As far as I know, nobody is building the hardware to do that yet. So I think, and also the first landings on the moon are going to be what we call a sortie mission. You land, you do some experiments, and then you leave. So they will just be sorties. When do we start building hardware and leaving things behind that we want to return to? I don't know. I hope it will be soon. The European Space Agency, under the previous director, I forget his name, Werner somebody, was very interested in building a lunar outpost. In fact, there was more work going on in Europe than in the United States for lunar outposts and space resource utilization and space mining. I think it's about equal amount. There's the same amount in the United States as there is in Europe. I have colleagues in Spain, in Luxembourg, the United Kingdom. People all over Europe are interested in space resources, and it's a very large community of people. And so I hope within about 10 years, we will be putting things on the moon to start building up an outpost. So I really hope we will start to build landing pads within 5 to 10 years. And that means we need to be developing the technology right now.
Yeah.
So,
Yeah.
and there is some funding. There is some funding, but I hope that there will be increased funding as we continue. We can keep doing these technology prototype development, field studies, and economic comparisons, and eventually down select to one preferred method, and then perfect it and build flight hardware, and then actually start to build landing pads.
That's fantastic. I hope so. I am not going to take more of your thought that I already taken. So thank you very much again, Phil. Has been fantastic presentation, has been excellent work, pretty honest one. And you say this, we don't know yet, but we need still to work on this. And you have opened so many questions and so many possibilities for us to think about that we will be eternally grateful. Okay. So probably I will send you an email with more questions in the next few days. And in any case, it has been a pleasure. We hope to meet you again in more, let's say, normal circumstances, probably inviting you here to give a seminar and to help our PhD students. We have among us a PhD student who is beginning to study the possibilities of mining in the moon and in the near Earth orbit asteroids. So, but he's not with us anymore, I think. He left. But probably it will be very nice to have someone like you around here. So we will probably invite you in the future.
I would be happy to do this again. It's been my pleasure to be here today. By the way, I have a friend who lives in Madrid who does asteroid mining. I don't know if you have met him, but it's Jose Galash. Jose Galash, and I can send you an email introduction to him if you would like. If you email me to remind me, then I will do that.
I will do that. I will do that. Thank you very much. It would be useful for these PhD students probably to have someone here in Spain who knows what we are talking about, at least more than me.
He's one of the world experts on this, so I'll be glad to give you that introduction.
Thank you. Thank you very much, Phil. I will send you an email to refresh that then.
Okay.
And it's been fantastic. Hope to see you soon. Phil,
okay.
Thank you very much again.
My pleasure.
Bye.
Bye-bye.
Bye. Bye.